This podcast is made possible by the Lighthouse Foundation for the Blind San Francisco, part of the Holman Journey 2019.
Roy Ryan is a PhD student in mechanical engineering at the Technion Physics faculty's Gamma Ray Sensor Lab. His work comprises of assembling salt crystalline sensors in a geometrically stable frame, an essential component for capturing gamma ray bursts emanating from multiple locations in the sky at undetermined times and frequencies, which requires ultra-sensitive crystalline wafers disposed in a spherical pattern. Roy has spent part of his master's at UC Berkeley and has taken research positions for the assembly of multiple sensors destined to be integrated in current and future NASA orbital satellites.
So this is the laboratory where you're actually working on the gamma ray sensors?
Yes. So this is our part of the lab.
Yeah.
We work on. Did I will tell you anything about the project?
Very basically, it was really just that you were working on gamma ray sensors.
Right. So that's in terms of space application. Then.
Yeah.
We're working on detection of gamma ray bursts. Gamma ray bursts they're called the most powerful explosions in the universe.
Very high energy explosions.
Yes. In gamma radiation, from neutron star mergers and supernova explosions, and there's a current problem in gamma ray detection.
Yep.
That it's hard to locate the origin of the burst.
Yeah.
Because all gamma. Your background is computer sciences and electrical engineering or computer science.
Computer science.
Just computer science.
Yeah.
Okay. So, in terms of the detectors are only all detectors are omnidirectional. All they detect is incident energy of photons.
Yeah.
And their sensitivity is largely independent of angle of incidence.
Okay. Yeah.
So obviously a single detector can give you no spatial information.
No spatial information. Yeah.
So what we were working on is getting spatial information from configuration of detectors.
Okay.
Classically, I'll show you what currently exists.
Yep.
So that's one detector.
Okay.
And this is a system of 4. The part at the back is the light sensor,
Yep.
which is a part of the. These detectors they're called scintillators when they interact with when gamma rays interact with them.
Yep.
The scintillators are hidden inside the casing.
So, yeah.
When the gamma rays interact with them, they emit a bit of light, and that light is detected using the photomultiplier tube, which is the circular thing at the back. This is not very different than what exists today. So you take a bunch of these detectors, and then based on relative counts, based on which way they turn,
Yep.
you tell the general direction of the burst.
Yep.
We're working on something that we think would be better.
Yep.
So instead of working with photomultiplier tubes, which you've just felt offering, so we work with silicon photomultipliers. So that would be a crystal, and the silicon photomultiplier
Yep.
is what you're holding. This is the wire, so on it.
Yep.
You can feel them on the crystal. They're very small by comparison.
Okay.
The crystal itself is also small.
Yep.
And what we're working on is building a compact configuration.
Yep.
And we're hoping that, based on simulations, the compact configuration is going to be much better than the existing thing.
Existing one, yeah. Well, maybe you could have higher density, maybe, like because of the compactness of.
We're all looking for density of detectors.
Yeah.
Yes. Or we're looking for a compact system. So right now, in the lab, we're in the middle of I mean, we're going to do some tests on the existing system,
Yeah.
which is using the older technology.
Yeah.
And then we're already building the new system.
Yeah.
And once the new system is ready, we'll test it and compare.
So how do you test and compare? Do you actually simulate?
I have simulations, so
Okay.
a lot of things I simulated. That's why I know what I'm looking for, and
Yeah.
I know what kind of system to build.
Yeah.
But now here we're working on actual testing in the lab. So I'll have, I don't have it here. I'll have a powerful source.
Yeah.
And I just point the source at the detectors, and I ask the detectors to pinpoint, like I use my algorithm to pinpoint it's just maximum likelihood.
Yep.
To pinpoint the location
Okay,
of the source.
Yeah.
And then I'll just show that the error is on the maximum likelihood estimator
Okay.
for source location on the older system is much worse than the new system. That's all I need, basically. Even though the new system is going to be smaller than the old system.
Mm.
So even though, like these detectors, the one you're holding is even bigger than the ones we're going to use.
Yeah.
So even though we're making our detectors smaller, I still think we're going to get better results.
Results out of it. Yeah. And well, you have an array of these. I guess.
We'll have, yeah.
Yeah. So the geometrical shape that you've chosen, like that has been chosen here. This is kind of it's like a low. I guess it's a low resolution sphere, right? Basically.
Kind of, yes.
Yeah. So in the new one is kind of the same thing. You're gonna take the same shape, or you just gonna
You don't have to
replace
take it. You don't have to do anything.
Yeah.
I'm going to try to create the most sort of the most dense configuration I can.
Oh, yeah. Cool. That sounds really cool. Yeah.
And that's it. This was chosen when it was part of a NASA mission that is now discontinued.
Which one?
It's called the ISS TAO.
ISS TAO. TAU.
TAO.
TAO. Oh,
Yeah.
TAO. Okay.
It's there was a mission for a wide field X-ray telescope with an accompanying gamma ray detector.
Yeah.
So this was supposed to be the accompanying gamma ray detector.
Okay.
But they discontinued the X-ray mission, so the accompanying instrument was obviously discontinued as well.
Mm.
We took the opportunity and said that now that we're not coupled to NASA, we can try things that are a bit newer, more experimental.
Yeah.
So we moved to silicon photomultipliers, which,
Yep.
as you can, you can feel, are much smaller.
Much smaller. Yeah.
That lets us actually make. I can't make a compact. This configuration is pretty much as compact as it gets.
Mm.
The older one, because the photomultiplier tube is about 10 centimeters long, maybe more.
Okay.
But the silicon photomultiplier is half a millimeter.
Half a millimeter. Okay.
So-
It's, yeah. It's way more compact. It's funny you're talking about how you can go a bit more experimental when being decoupled with NASA, because there's someone at NASA who spoke about the engineering requirement matrix that they have, which can exceeds 95%. Whereas when you have, like, for instance, an environment like a lab like this, or startups and things like it's only actually about 51%, and at 51% you can proceed with trying, like, maybe a new form or a different version of what you already have. Whereas at NASA it's like very, very difficult to get that actual access to the next step of a project. I mean, that's what I heard from
Yeah,
people from NASA.
they require a lot of. They require everything to be well proven.
Yeah.
And yeah, this is the silicon photomultiplier, the one you just. And that's the board on it.
Yep.
So if you feel that there's probably on the board, there's probably going to be a smooth surface.
Yep.
So on the other side,
this
so
side,
yeah,
yep.
yep, there we go. That's the silicon photomultiplier. It's 6 millimeters by 6 millimeters by half a millimeter. So, and that's the light detector. That's all of it. As opposed to
very
the,
small, yeah.
as
And
opposed
so this is a battery?
no, that's a
No.
scintillator.
It's a scintillator.
That's a crystal.
Okay.
It's actually salt.
Yeah.
Cesium iodide.
Yep.
And it emits light when it's covered in Teflon because I want to trap the light inside.
Yeah, inside. Yeah.
Except for when it.
I suppose just-
That's the output for the
Yeah.
signal.
Yep.
And the other line is power. It takes about 30 volts.
This one.
Yep,
Yep.
that's power supply.
Hey Jake, you see this? Let's start doing these later. No, Jake is he's the electrical engineer in our team. He does most of the hardware and stuff.
Mm-hmm.
He'd be kind of fascinated to actually be here to see this. Is it?
Oh, sorry. That one is that's one of the sources. The weak sources.
Yeah.
It's covered in lead, so
Okay.
no worries.
Is it possible to put Cosmobot take a picture with the little character that we have? There?
Mm-hmm.
And so these would normally be deployed like with a local satellite or like a local spacecraft?
We want to put them on a nano satellite. I mean, okay. So the plan is, because of budgetary constraints,
Yeah.
to put them on nano satellites. I would really like to build a full scale system.
Yeah.
So the plan is for a 10 by 10 by 10 centimeter configuration, but
Yeah.
I would really like a larger system.
Yeah.
Because I think with a larger system, I can do, with a small system, I can do the same thing that people do today,
Yeah.
only a bit better.
Yeah.
With a larger system, I can actually do new sounds.
Yeah.
So I really want to deploy a larger system
Yeah.
that doesn't always, doesn't always work.
Hmm.
But I'm hoping that once we get our detectors going in the lab, and I'll prove that my concept is
Yeah. Will be
better.
Yeah. Is kind
Then-
of more scared. Yeah.
Then yeah, I can publish those results, and hopefully can get interest in maybe getting it attached to a big mission.
To like a future mission.
Yeah. So there's always future missions going up.
Yeah.
And this thing, the entire system is a big system is gonna weigh like 6 or 7 kilograms.
Okay.
It's a bit big for a detector system, I guess, but it's not. It's not it's not unheard of. So
Well, some of this like what's the last what was it called? Is it Swift? No, not Swift. It's Fermi, right?
yes, the Fermi GBM.
Yeah,
Fermi GBM uses technology that's similar to the old one. It uses 12 scintillator crystals
Yeah.
that are exactly bigger, but exactly the same ones that are on my table at the moment.
Yeah. How many kilos is that payload?
For Fermi?
Yeah.
Well, Fermi's LAT is, I think, the big payload,
Yeah.
not the GBM.
Not the GP. Okay.
But the GBM would be. So let's see. So each of these should be. So they're 5-inch cylinders.
Okay.
5-inch diameter cylinders and a 1/2 inch thickness.
Okay.
And the density is 3.5 grams per square centimeter centimeter cubed.
Per centimeter cubed. Okay, so that's
So it's kind of like it's about
so it's
5.
Did you say 5? Yeah.
So it's about 5 times 2.5, which is it's about I think 7 squared, about 50 times. So it's about I think probably something like each of these detectors would probably be something like 1/2 kilo.
1/2 kilo.
And there's 12 of them.
Okay.
So,
Alright, so
maybe a bit more than 1/2 kilo. So 12. So so it's something like that.
Okay. Yeah. So a bit over 6 kilos.
Probably a bit more. Probably more.
Yeah. 8 kilos. Okay.
I think, like off the top of my head.
Yeah, I mean, if yours actually has a higher density,
Mine, the fuel. What?
yours would have a higher density.
Yes,
higher
my
density, yeah.
TC iodide is 4.5
Yeah.
grams, and the other one I want to use, which is GAGG,
Mhm.
is 6.6.
Okay.
So yeah, obviously, and higher density works better.
So what initially sparked your wanting to actually do this work?
So I actually got in working on the mission for NASA with Elle, because I wanted to work on something for space,
Yeah.
space instrumentation,
Yeah.
and that was just getting into the next phase. So I got in on, I joined that,
Yeah.
worked on that for a year, and then when they scraped the project, my colleague who is no longer here said, told Elle, look, we can do our own thing,
Mm.
and then that's how that started.
Okay. Yeah.
I went to Berkeley to work with the person who writes simulations
Yeah.
for these things, to learn from him.
Mm-hmm.
He gave me some ideas. I came back and made simulations to test these ideas.
Yeah.
And now, I mean, my simulations show that I can get something that, according to my simulations, I'm going to get something that's, phenomenal. Now,
Okay.
I believe simulations,
Yeah.
but I'm always careful. So,
Well, I guess like in the past 13 years of monitoring the sky, there's only like 512, 518 gamma bursts.
no.
No, there's more.
So in the 90s, there was BATSE
Mm-hmm.
between 91 and 2000, which
Yeah.
detected 2,700
Yeah.
gamma ray bursts. It was a huge detector. It was huge.
Yeah.
And then Swift Swift has currently, I think, the best resolution,
Yeah.
spatial resolution,
Mhm.
but it only sees a relatively small portion of the sky.
Okay.
2,500.
2,500.
Yeah, it's sort of an 2,500 gamma ray bursts.
In 10 years. Okay.
Yeah.
That's cool.
That's about one a day. It's
Yeah.
about one a day.
About one a day. Okay. Yeah.
That's the rate.
Yeah.
Although they don't see the whole sky, but they see a lot of the sky.
Yeah.
They see most of the sky, but their angular resolution is not as good.
So they don't know
Nearly.
exactly where it comes from.
I
I mean, you can sort of do an approximation, by actually.
the approximation though
Approximation, yeah.
would be bigger than the size of the constellation on the phone.
The size. Oh, really?
Way bigger. Way bigger.
Wow,
I'm
that's low
hoping-
resolution.
Yes,
Yeah.
I'm hoping to reach. Let's say if I can pinpoint the location of a burst to say the size, similar size of a constellation that you
Yeah.
shown me on your app,
Yeah.
that would be good.
Okay.
Swift can do much better, obviously, and Swift will always be able to do much better.
Yeah.
Swift can only cover a small portion of the sky at
Yeah.
a given moment. It's always a trade-off.
Yeah.
I just think I can make the trade-off better. That's it.
Okay.
But and I mean, my simulations support that. I don't want to claim success where so far I haven't had any. It's only theoretical.
Yeah.
But hopeful.
Well, if you have if you have a denser array, basically you can sort of do some kind of convolution network
Right now
using your array.
I'm just using maximum likelihood estimation.
Yeah.
And it's basically I'm making it work like. So you can do what you do in Swift. You do a two-dimensional mask.
Yep.
That blocks portion of the sky, and thus based on sort of based on the on which detectors are activated.
Yep.
On Swift, you know where the burst came from at a very high resolution. You can't do that with scintillators.
Yep.
So Swift is sort of like a Swift bot is sort of like a camera
Yep.
for gamma rays. What I'm trying to do is something like in the middle.
Mm-hmm.
I'm trying to make my detector be sort of half a mask, half a detector, where the detector is its own mask.
Yep.
So it's basically, what I'm basically doing is creating a bunch of voxels.
Okay. Yep.
And then based on the voxels, I reconstruct the origin.
Okay, so yeah, it's a what's a cubic matrix basically.
Pretty much.
Yeah, but like, is the output of each of these, is it like stable in terms of, like, is it does it have variance
In what way?
in the output? Like, let's say when you take like a burst,
Mm-hmm.
but you keep repeating the same burst at the exact same energy level, let's say in your simulation, right?
Yeah.
Would it pick up the exact same measurement every single time, or
No.
is there a bit of variance?
No, there's a lot of variance.
There's a lot of variance.
Because so each of so there is I mean, burst is kind of, I guess, misleading.
Yeah.
They're very highly energetic,
Yeah.
but they're also very far away.
Yeah.
So let's say a burst can be 5,000 photons total.
Yeah.
And if you have, so if I have like 50 detectors, 5,000 photons means 100 photons.
Yeah.
On each detector, that would be a burst.
Yeah.
So, and this could last a few seconds.
Yeah.
So that means that there's a photon every few milliseconds.
Yeah.
Yeah.
So. Okay.
And so, and so it's since it follows a Poisson distribution,
Mhm.
you're gonna get a lot of variance in when each photon arrives.
Yep.
And which photon arrives.
Yeah,
Which energy.
horizon.
If you sum up everything and it's an exact burst, you should get a spectrum that's somewhat similar.
Yeah.
And within the resolution error, spectral resolution error of the detector,
Yeah.
which in itself is rather big. It's 10%.
Okay. Yeah. So it is 10%. So like that was my question. Basically, if you took a burst and then the next burst was literally identical to the first
in
burst.
terms of spectrum.
Yeah, in terms of actually absolutely everything.
Oh, then in terms of spectral resolution, it's 10%. That's the easiest part. In terms of spatial resolution, that's an open question. Fermi GBM report that for strong bursts they have a 15-degree error, average error.
Yeah.
Swift bot have, I think, 4 arcs minutes.
Yep.
But like I said, it is a smaller part of the sky.
Mhm.
Hoping to be in between, hoping to have only a few degrees.
Okay.
But again, that's my hope.
Yeah. Well, that's really cool. It's a really cool project, and on top of that, it's for space.
Yes, I'm a sucker for space. I want to work on, it's what I want to work on.
Yeah. Yeah. That's sort of what I've kind of really turned my attention to mostly now. Obviously, I do computer science, but I'm more focusing on machine learning. And using machine learning to kind of give me better kind of indication, I guess, like automated guidance to the things that I want to do by using examples, obviously supervising and unsupervised learning. I guess it's very different, like, from building and constructing things. But I do think that,
I do code for these things all the time.
yeah. What language do you use for this? I'm guessing C++.
No, so for the boards themselves, for the embedded, we use embedded C.
Okay. Yep.
I used embedded C. I immensely hope that next time we use something else because it's difficult.
Mhm.
For also my simulations and data analysis, I use Python.
Yeah, Python's the best.
It has
Absolutely.
because whatever I need, there's already a library.
Yeah, always. Yeah, no, all my data wrangling and like all the database cataloging and stuff like that was done in Python. And, you know, it's the best language for that kind of stuff.
Yeah, or you use further than data analysis, I use Python.
Yeah,
Yeah,
definitely.
and for embedded, you use embedded C. Unfortunately, I hope that the next time we work on something good, I could be able to write it with something, you know, a little less low level.
Yeah.
But can handle embedded C if I have to.
Yeah. C is something that we all need to handle. Leah, do you want to put Cosmo Bali there?
Already there.
Oh, she's already there. Have you
Snippet.
taken a picture like of an angle that kind of looks nice?
So
Yeah.
so what's that?
So Cosmo Bali is part of for the kids. What we're trying to do is she collaborates with us. Her name is Fia, and she has done a set of coding kind of applications for blind kids, blind children, so that they can learn coding from an early age. And the thing is called Bali Land, and Cosmo Bali is kind of like one of the new characters of that Bali Land. And so what we're doing is, as we go across the world, we're putting Cosmo Bali in different places as a postcard kind of stuff. To kind of say, it's really kind of to inspire the kids to do the STEM subjects.
Joking, that's admirable.
Yeah, because one of the big issues when you're blind is that society tells you, oh no, you're blind, you can't do this, you can't do that, and especially in the STEMs, it's a big issue because you have a lot of kids who want to do STEM, but then people just say, no, it's too hard for you to do something else. Whereas I don't know, I tend to think like if you challenge yourself in life, then you get rewarded. Whereas if you take second or third choice in your life, you're not going to get to where you want to go. So it's that kind of inspirational message we're trying to send to the kids, and also their parents, and their and their peers to kind of say, well, maybe after all they can do it. If this guy and other people can do it, then my child can do it. So yeah, that's the idea.
Good message.
Yeah.
So what are you doing with the? I noticed you're recording. What are you doing with the recording?
So what we're going to do is like for gamma ray bursts and also for analyzing like the the morphology of jets, which is what Ehud's kind of speciality, right? We're trying to. I'm going to take notes to see where. Because I've downloaded like the papers, I've read the papers, I'm kind of classifying everything, and I'm trying to see if I can find all the APIs and data streams.
Okay.
And so there's a large list of spacecraft out there, with the instrumentation. They're all kind of standardized under one format, the FITS file format.
Right. Yes.
And I'm able to actually parse the headers of those FITS files and see
there's a Python library for that.
Okay, there you go. So I'm just categorizing all of that and then kind of I'm trying to set a new feature where, say, when you look up at the sky, you create a region with your fingers, like a rectangle.
Right.
And then it will stream in every, it would find, right, every instrument out there for timeline T, n to n plus whatever, of that specific region, and just put it on there and compose all of the available, frequencies in the spectrum. So whether it's going to be light or infrared, near
That would be useful anyway.
UV, gamma.
I would need something like that.
Oh really?
Yes.
Oh cool.
It's very. I really like multi-messenger research.
Yeah.
Multi-messenger physics.
Yeah.
I almost both my previous paper and the one I'm working on right now.
Yeah.
I'm using. I'm trying to use multi-messenger when I can.
Okay.
So it would be good if I could look at something and know
what's happening.
what wavelength
What
you could
wave-
look
yeah.
at, and it's difficult at the moment. You have to start searching the literature,
Yeah.
and each of these instruments have their own standards for reporting.
Well, the engineering,
Some-
yeah,
Some of them are semi-closed or closed.
yeah,
Yeah, it's not easy. It's not easy. So that's a tool that's going to be useful anyway.
yeah.
Um,
Well, I thought it would be really kind of good, to be able to see all of the different spectrum. And
yeah, and for the
yeah,
double
yeah. And I don't think it exists.
does not.
Yeah.
Not as much. Not. I mean, I don't know that it does.
Yeah.
When I was trying to cross-reference observations, that was very difficult.
Yeah. Huh. There you go. There you go, guys. Astrios is actually a good project to
Oh yeah.
yeah, continue on and yeah. Because that allows, I mean, if I do it not out of convenience but out of necessity, it probably also trickles down to something that will be convenient for other people, because I'm fundamentally trying to just access the information in the best way possible, and so that's my fundamental necessity. And then from there, if like some of the things can trickle down to to other use cases, and that's really cool.
So I can tell you from my perspective,
Yeah.
it would be very good to get there's a need. I've learned that you can get a lot of information from when you compare results in different wavelengths,
Yes.
and unfortunately, it's not actually being done enough. So
Yeah, I agree with that.
So I would actually really like to see something that allows easy access to.
Yeah.
I'm looking at this object. I want to know if anybody looked at it in
Yeah.
infrared or optical or radio band.
Radio band. Yeah.
Yeah, because I work X-ray right now, for example.
Yeah.
Rather than gamma ray sometimes, and I work X-ray likelihood.
Yeah.
So I look at something. I look at the Cirrus galaxy, and I want to know had people looked at it in optical or in IR or near UV or radio or microwave or whatever.
Yeah.
Right now it's kind of difficult. You have to start looking for papers manually.
Yeah. Yeah. Well, I really kind of looked into all of the.
Huge project though.
Well, I started the project like just the interactive augmented reality part. That was 2 years ago, but since last year I've been working on the how to aggregate all of the data, where from, and how to shift the timelines, and what to do when there's no time. So for instance, maybe let's say TESS as timeline t plus n, and then you got like maybe Kepler, which started at n minus 5 and then ended at n minus 2, something like that. So there's some overlaps in between the two, and what to do with those areas where it's empty, how to show it and display it, and for each of them, because each instrument has different spectrum. But if you look at the header file of the FITS file, then the header gives you a lot of information. What I did is I parsed to really kind of take all of the the combination of everything that exists in the dictionary of words. So there's sections which are purely engineering, sections which are the internal instrumentations and sensors, their filters, their range of capture, and then I also have to check like the resolution of the images that come through, and then kind of perform the proper either cropping or placing, masking, scaling, things like that, to unify all of the streams that come in for each of the instruments. But because there's a central repository, which is the mass repository, which takes the most up-to-date information, I'm actually able to do that. So it's work, but I like that kind of work.
Okay, great. I mean, it's a big project, but I think it would be good if it is.
Yeah. It is a big project, so if anyone is interested in helping us out, give us a shout out. Well, thanks a lot, man, for this.